Well, looks like we're just about there, folks. Let's run the clock just to make sure no one else is coming in. But it might be one of those days where it's just the few of us. We'll make it work either way. Any questions at all before we start out? Okay, well, let's run through the announcements. We're nearly done with section 5.3. After we move through that section, we'll be in section 6.1. But that's an odd spot for us. Well, I mean, it's odd in a good way. Assignment 22 has to be the last assignment of the semester because we'll finish 6.1 possibly next Tuesday. And I can't give a homework assignment because I don't collect homework on finals week. That just doesn't sound like the right thing to do. So this will be the last assignment. And for any other sections that we covered going beyond section 5.3, what I'm going to be doing is post suggested exercises out of the book, and I'll post the solutions as well so you can get some practice. But I think 6.1 might be our, in fact, last section of the semester. That might make sense to stop on that one. We'll see where we end up and make a determination at the end of class today. So that means on Tuesday, we're just going to tie up anything we're finishing up on, say section 6.1 again. After that, we're going to immediately convert to reviewing for the final exam, and we'll do that again on a week away, the 25th. So we're just about there, folks. Any questions at all at the moment? Okay, so homework is about done. That's kind of cool in a way. We've had, let's see, 22 homework assignments. That sounds extreme, but that's just because they were on a section by section basis. And the next thing to talk about is there are several extra credit opportunities available to you, one of which I think we've hinted at before. Let's talk about this one. If you had a rough exam, I think that's kind of typical in this class. Chapter 4 just has a way to kind of not make you feel great about linear algebra until you move through it. So if there's an off day you had, or maybe work got busy, one of those exams is a little bit rough, the final exam score will replace your minimum score among exams 1, 2, and 3 if your final exam score is higher. So that's a pretty substantial extra credit opportunity there. And I got a habit of giving this extra credit opportunity because it turned out over the years, giving like an extra assignment didn't really help people out, but I encourage people to study for the final exam because of that. That seemed to make the most difference. So I think that's the most pivotal extra credit opportunity there. For another one though, I am accepting late work this semester. So if you go through your grades in the grade book in Moodle, if anything's missing, then I will accept those for full credit. The day of our final exam, April 30th, would be the last day I can accept it, but that's potentially a substantial amount as well. The other one is through course evaluations. And the way this one will work is we are dropping 2 assignments this semester, your lowest 2 assignments. And if you complete the course evaluation and email it to my ICU email account, I'll drop an additional 2 homework assignments. That's quite a additional extra credit there. And the reason for that is, turns out the math department's been having a really hard time getting course evaluations for the classes. I'm not completely sure why, but for one reason or another, they've been struggling. So I've been trying to give extra credit for it just to see if we can get more course evaluations. You don't have to do the evaluations. That's something I have to be straight up and honest about. So if you'd rather not, that's completely fine with me. But yeah, exactly. And if you've already done the evaluation, just go right back into it and it'll say you've already completed it. That screenshot works for me as well. Just send it to my ISU email address and you'll get the extra credit. How do you get to that? That's a really good question. I think that's why the math department's been having trouble. Well, I don't know. This would be something that other departments figured out, but not the math department. It's right here. So there's a whole system of tools and things inside Moodle on that left arrow button. So if you click on that, there's all sorts of things like upcoming events, announcements, recent activity, and it's buried there right in the very bottom. Doesn't seem like really great design, but I think we can fix a little bit of that. Let's move this to the very top now. See if I could actually get that there. Okay, so now it's, if you open the block drawer, this little thing, course evaluation pops out. Click on it, and this is what it looks like. And this is probably another approach where the math department went wrong. They're trying to get more course evaluations, so they write this really long paragraph of why you should do it. I don't think that's the best approach, to be honest, but that's what they did. The reason that math department wants course evaluations is because the State Board of Education wants them. We're a state college, so if the State Board of Education says to do something, we absolutely have to do it or everyone gets fired, basically. So again, it is completely up to you. You don't have to do these evaluations. If you decide to, click on this link here. I think it takes about 10 minutes, maybe 15 minutes if you're putting in a lot of detail on average to go through it. And then again, just take a screenshot of the completion page, send an email to me, or even a cell phone picture of it will do just fine. And I'll drop 2 additional assignments at the end of the semester. Any questions about that, folks? Okay, we have a really good question on where is it even? I think there's a lot of things that they could make a little bit easier on that, but there it is. It's totally optional, but it does have extra credit attached to it. Let's go back down here. I think that was most of my announcements. Other questions so far?
Is ISU switching to Canvas in the fall?
We are, yeah. So I think that's another thing that we've been kind of upset about. Moodle has been great, but we've been using it for so long that it's starting to get clunky in modern times in 2024. So I guess we're hoping Canvas works better. I'm not excited, but again, that's just something that they make a decision on and we all have to figure it out. Hopefully it's not too bad. So we'll see what it looks like in the fall. Other questions about that so far?
Does it also go backward if you have like some previous example of final?
Oh, what do you mean backwards? Sorry.
Like there's a first, second, third example, it's lower than the final.
Mhm.
Final is in the place.
Yeah, exactly. That's what it'll do.
Backward.
It will work backwards. Yeah. So this won't hurt you potentially. Is that what you're
It
meaning?
will work backward or?
It will not. Yeah. So for example, some quick examples.
I mean, if the final is lower, it's not going to replace.
It's not going to replace if the final is lower. Yeah. Because that would hurt your score. Sorry, say again.
The final is lower, it's not going to be replaced by
By other exam.
you have higher score of the first or second exam or the third one.
Oh, no, you would keep the final exam score. I see what you're saying. Yeah. Sorry, it was kind of mixed up. Yeah. Yeah. So your final exam score will just stay as your final exam score. But all it could potentially do is wipe out a lower score amongst exams 1, 2, and 3. Yeah. Thanks for that question there. It took me a minute to understand. Other questions so far? Okay. And then maybe the last thing to discuss for the announcements are our final exam is going to be in this classroom, 5:30 to 7:30 p.m. It'll be like we're coming in for a normal class, but we're just going to hang out for 2 hours, rough writing things down, that and such. And I guess I don't have too much to say about that. There's some sample final exam problems down below, but these have been available all semester. This is kind of an old document, so I don't push this one too much, but if you want additional practice, this is a really great place to go. I think I wrote this in like summer 2015 when I taught linear algebra over a summer semester. So lots of good stuff inside here, but I'll be posting more materials. I want to post a good actual real final exam so you'll know what a 2-hour exam even looks like for a class like this one. It's not going to be like before where it's 20 questions, many of them which are concept questions. It's going to be more around 12 to 16 questions. Some of them are a little bit longer, some of them slightly faster, but you'll get a good feel for it once we start posting those documents. You'll see more materials here before you come to the Tuesday's class. Well, I think I ran out of things to say for announcements. Any other questions, comments, concerns, or otherwise? Okay, well, let's get back to section 5.3. We're working on diagonalization. After that, we'll look at some geometry of vector spaces in section 6.1. But before we take a look at example 4, let's remind ourselves what we're even doing. That's always a good thing after a weekend. What we're trying to do is diagonalize a matrix, which means we're producing a matrix factorization. A matrix A can potentially be written as P times D, where D is diagonal, times the inverse of P. And that's our diagonalization. But there is so much more to say about that. Once you look at theorem 5, it's telling us even more. Your diagonalization happens if and only if you have n linearly independent eigenvectors. And that means once you find those eigenvectors, like say in this diagonalization, this is P, this is the matrix D, this is the matrix P inverse. It turns out that eigenvalues of A go on the main diagonal of the diagonal matrix, and the corresponding eigenvectors are right here on the matrix P, as well as on P inverse, since we're just indicating it with the inverse, not actually calculating it out, just saying invert that one. And just another reminder, on a real exam, the final exam, you never have to calculate that inverse, not even on the homework. You can just leave it in that format. That's like a whole separate question. So that's kind of nice. The moment you have a diagonalization, that means you know what the eigensystem is, the eigenvalues and the corresponding eigenvectors. And to diagonalize something, that means you've got to start off by finding all the eigenvalues to begin with. So you take the determinant of this characteristic equation. Once you find an eigenvalue, you now have to find the eigenvector, or the basis for the eigenspace. So for this one, it had basis 1, 2. Do it again for lambda 2 equals 1, which means you're just solving this equation here. That was our next eigenvector. These two are guaranteed to be linearly independent. That's kind of a nice fact. If they came from different eigenvalues, they're automatically linearly independent. So we just throw them into a matrix here. But be careful with the correspondence. If you put -4 here, then that means 1, 2 has to be the second column. You could change this around. -4 could have been right here, but that means this column has to move over to here as well. So as long as you have things in a correspondence, you're all set. There's lots of different ways to write the diagonalization. Well, that's a tour of what we did last Thursday, or last Tuesday, rather. No, that was last Thursday before the exam. I'm forgetting what we were doing. But any questions at the moment? Okay, well, let's try it all over again. Here's a brand new matrix. It says diagonalize the matrix or explain why it's not possible, just like on the last example. But there's a bonus on this one. We don't have to actually calculate the eigenvalues very hard or put a lot of effort into it. We can just state them. Anyone see what they are just by visual inspection? Exactly. This one's lower triangular, and that means the main diagonal contains your eigenvalues. Good call. So it's 2, 4, 2. But notice there is a repeated eigenvalue. That's already kind of special on this. Lambda 1 equals 2. In this context, we would say has multiplicity 2. Because it showed up twice in that main diagonal. For the value 4, it only shows up once. And so this one has multiplicity 1. And when it comes to determining if your matrix is diagonalizable or not, you always want to start at the highest multiplicity. And here's a reason. If we get 2 linearly independent eigenvectors out of this, if the eigenspace is of dimension 2, we can diagonalize it. But if the eigenspace for this is of dimension 1, we cannot. You wouldn't want to find the eigenvector for this one because that's wasted effort if it's not diagonalizable. Start where it could go wrong first, and you could save a whole bunch of work. So that's a good comment to put on paper. Always start with the highest multiplicity. So we'll start with lambda 1 equals 2. Very first thing we need to do is take a look at what are the eigenvectors that go along with it. So if lambda 1 equals 2, that means we now need to solve a minus 2i x set to the 0 vector. I don't know why I put the vector symbol on x. That's a pattern breaker. I usually put it on the 0 vector to indicate it's not a scalar. So we need to solve that thing. That's where we would get our eigenvectors. This has augmented matrix that goes like this. you're taking a minus 2i, that just means you're subtracting 2 from the main diagonal. The rest of it's the same. So it'll go 0, 0, 1, 0, 2, 0, and 0, 0, 0. Here's the right-hand side from the matrix equation over here. And now that's our system to solve. It can be put into row reduced echelon form in just one step. Make row 3 your row 1, 1, 0, 0, 0. You can make your row 2 still, maybe divide it by 2, 0, 1, 0, 0. And row 1, let's make it row 3. And there it is. That's in row reduced echelon form, one step. That's kind of nice. But here you can get your eigenvector, except it'd only be one eigenvector, one literally independent eigenvector. And that's because there's a pivot here, but no pivot there. Let's say something about this right away. There is only one free variable. And that's important because what it tells us is the dimension of the null space, we're looking at a null space because we're setting this equal to 0. It'd be the null space of that matrix, A minus 2i, is equal to the number of free variables. There's exactly 1. And now we've got a problem. The algebraic multiplicity was 2, yet the dimension of the eigenspace is 1. We're only going to get one eigenvector. But if this is 3 by 3, we require 3 linearly independent eigenvectors. We'll never find them. So here we get to stop and say, since lambda, let me try again, lambda 1 equals 2 has multiplicity 2, but the corresponding eigenspace has dimension 1, which is less than that multiplicity of 2, we get to stop. There is no diagonalization to this. We would say just briefly, A is defective. Again, that's kind of the most interesting definition of linear algebra, in my opinion. Defective just sounds like something is terribly wrong with that matrix. And that's not necessarily true. It just means if this matrix came from an applied setting, something in engineering, for example, and you need to do something along the lines of differential equations, maybe partial differential equations, the moment you found that your matrix is defective, it means you're going to have to work really hard now on this particular problem because there's a lot of tools that are suddenly unavailable to you. Diagonalization has a lot of cool properties. But this would stop right here only because of that feature. Any questions at all, folks, with running through this problem? Okay, this is the danger, though. If we started with that value right here, lambda 2 equals 4, we will get an eigenvector, and you can't tell at all at that step if you're diagonalizable or not. It would have been totally wasted effort. So that's the purpose of starting with the highest multiplicity first. That will resolve if you can diagonalize at all. Well, any questions, folks, with the run through for this one? Okay, these are like the fun questions on the final exam because it just ends right here. But this is the reason the final exam is probably anywhere between, say, 12 to 14, potentially 16 questions if I have some fast ones. Because if it was diagonalizable, this is a process and it takes time to run through this. So the final exam could involve questions that go along these kind of lines. Well, let's move on to the next step. Oh, sorry, go ahead.
Yeah, just to make sure I have everything straight. So when you say lower, lower triangular.
Oh, yeah.
You mean that the upper triangle is all zeros?
Yeah, exactly. That's exactly right. So this is lower triangular because all the non-zero entries are below. Exactly.
Oh, gotcha. I was looking at it the opposite. That makes sense.
Cool. That's actually a pretty tricky definition, but the good news is, as long as you know it's triangular, that's the most important thing. The upper lower designation is important, but not critical. Other questions so far?
Also, like one of the pivots points is 0.
Mhm.
There's also gonna be like, one of the, eigenvalues of.
Yes, absolutely. If there was a zero here, that would have been an eigenvalue. And that's a really important question. Let's put this right here. If A is equal to 0, 0, 1, 0, 4, 0, 0, 0, 2, then now we can say some interesting things about this matrix. It's not invertible at all, right? That you have a lack of pivots due to that row, but the eigenvalues go this way. Lambda 1 equals 0, lambda 2 equals 0, or let me try again, 4, and lambda 3 equals 2. We have 3 distinct eigenvalues now. This is automatically diagonalizable because you'll get an eigenvector from each one. They'll all be linearly independent against each other. And so this is enough to say A is diagonalizable, that's such a long word, since it's 3 by 3 with 3 distinct as in all different, eigenvalues.
So you can skip to the end, if you have 3 ones that are different on the diagonal.
Exactly. Exactly. We can now diagonalize this matrix right here, which honestly is kind of unfortunate in a certain sense, because if it's 3 by 3, you have 3 distinct eigenvalues, it will be diagonalizable, but now you have to do this 3 different times to get to the 3 linearly independent eigenvectors. In fact, that's what we did right up here. Let me take a look. Oh, that was a size 2 by 2. We did it for each of the eigenvalues. We had to solve this system and get an eigenvector. For this one that's 3 by 3, you now need to do it 3 different times. Kind of tedious in a way. And it says preparing live stream. That's kind of concerning. Let's just hope the recording's still going. But maybe if I stop the share, let's see here. It's still going to YouTube. Sometimes I think Zoom just glitches out. Let's hope for the best. That just seems ominous, but I don't think we can make that disappear. The technology is angry today. It's probably tired. It knows it's the end of the semester. But other questions so far, folks? Okay, yeah, that's a really good question there. In fact, this is essentially a theorem, but there's another theorem that goes along with it. So if lambda 1, let's just say it this way, make it look like a real theorem. We saw this in section 5.2. If lambda equals 0 is an eigenvalue of A, then A is not invertible. So we could tell that already because we just saw that there's a zeroed out row, but in a different matrix where nothing is zeroed out, if you did come to that eigenvalue, you automatically know it's not invertible right away. So this is kind of strange because every time we got a new definition in linear algebra, what we expect to see is the invertible matrix theorem to grow, but it actually doesn't happen here. Diagonalization is one of the very first concepts in linear algebra where this doesn't even plug into the invertible matrix theorem at all. A can be diagonalizable when your matrix doesn't have an inverse, and it could still be diagonalizable if I put in, say, a 7 here, and now that matrix is invertible. So invertibility and diagonalization have nothing to do with each other, and that's kind of weird in linear algebra. We expect those things to be connected. So the moment we find something that does not plug into the invertible matrix theorem, that's exciting. That means you're forging some new territory in linear algebra at that point. Any other questions so far? Okay, well, let's keep on going down. And here's another one. It says, diagonalize this matrix or explain why it cannot be done. Well, we have the same kind of setup. Did we just do this one? Let me see here. No, that was example 4. This looks like deja vu. It is definitely a different matrix. The lower part is different here. Let's try this out again. So just like before, it's lower triangular, so you can identify the eigenvalues on the main diagonal. I would say this is not a guarantee on a homework problem, But this is typical on an exam question because I wouldn't want this problem to be so long, it's over multiple pages. I usually do give a triangular matrix on a real exam. So let's write out lambda 1, 2 has multiplicity 2. Lambda 2 equals 4 has multiplicity 1. Now, the last one was defective, but we still on this one want to try out the higher multiplicity in case this one's defective as well. Let's just see what happens. So let's start off with really just organizing. Lambda 1 equals 2 means we need to solve a minus 2i x set to the 0 vector. Becomes kind of automatic once you've done these a lot. This now just says go up here, subtract 2 from the main diagonal. So here's the augmented matrix. 0, negative 1, negative 3. 0, 2, 6. 0, 0, 0. 0, 0, 0. So there we go, we've got it. And it doesn't seem too different from this one right here, right? It looks kind of similar, except this one had 2 pivots, and that blocked it from being diagonalizable. On this one, let's just do some row reduction, see how many pivots we have. What we could do is just automatically multiply row 2 by negative 3, add it to the row below. If you did that, this is all gone. That'd be a positive 3 times negative 3, so it's 0. This would be a negative 6 added to positive 6, so it's 0 as well. You can just think of this whole row as being gone at this stage. So there it is, it's gone. Next, I'm going to multiply this row by negative 1, bump it up to row 1. So 1, negative 2, 0, 0. Now, row 1 could be our new row 2. So that was like 4 or 5 steps all at once. Does it make sense to get to that stage? Awesome. This is the point in linear algebra where we get a little bit better at row reduction. So if you're taking a whole bunch of shortcuts on your homework or an exam, I'm totally okay with it. So if you see nice shortcuts, definitely take them. Next thing we have to do is, well, observe there is 1 pivot right here. And that means the dimension of null a minus 2i, it's the number of free variables. There's 2 of them. So it's dimension 2. Let's just tie that idea together. Number of free variables. So that means, well, if this 2 here matches the algebraic multiplicity, we can diagonalize A. Let's say here, A is diagonalizable. Wish we had a shorter word for that, but it makes sense at least of saying diagonalizable. So now we need to solve the system. X1, X2, X3 are the variables. Now all we're doing is a chapter 1 problem, section like 1.5 parametric vector form. On X1, we'll solve that to say it's equal to 2x2 for x2. That one's a free variable, so x2 is just x2. X3 is also free. X3 is also free, so x3 equals x3. Then this implies this x right here, our whole goal is to solve for it. And we can say x equals, I don't think I can fit it right there. Let me try moving it over. Down here. So x equals, take out the parameters x2. We have coefficients 2, 1, 0 relative to that one. Next parameter is x3 with coefficients 0, 0, 1, where x2, x3 are in R, so any scalar. So that's the parametric vector form. But one thing that we wanted was not necessarily the full description of the solutions. It's all about the constant vectors. So we can now say that for lambda 1 equals 2, our eigenvectors are going to be v1, 2, 1, 0. And there's infinitely many choices. What I did was I chose a value of 1 for this scalar. So this is 1. Chose a value of 0 for that scalar. So 0 there. And we get 1 eigenvector. The next one is V2, and same trick, you're just grabbing the scalar, or excuse me, the constant vector. So V2 will be 0, 0, 1. Well, that's halfway through the process. Any questions, folks, to that stage? Okay, we have to come back to here. So I'll just put a little bracket as a reminder. Wouldn't want to put a box on it because it's not the answer. And in this country, a box usually means you're stating an answer. Let's do the next one. We need a screenshot first. Somehow I thought that'd fit on one page, but I think we're going to need multiple pages on this. Next thing we do is just go to the other eigenvalue. It was lambda 2 equals 4. So that means we're solving a minus 4i, x set to the 0 vector, which means we're going to the augmented matrix, where we subtract 4 from the main diagonal this time. So that will be a negative 2, negative 1, negative 3, 0, 0, 6, 0, 0, negative 2, and 0, 0, 0. Well, A was of size 3 by 3, and we've already found 2 eigenvectors. That means this one should have 2 pivots. There should only be dimension 1 for this eigenspace, for the one additional eigenvector. I think the cleanest way is multiply this by negative 1, make it your row 1, so it's 1, 0, 0, 0. But at the same time, if there's a 1 here and 0's to the right, it immediately kills off everything above and below. So this becomes a 0. Now let's make this whole 0 row our row 3. What else can we do? Well, we can take this row right here, or this one, either one you'd like to visualize. Let's say this one right here. Multiply it by positive 3, add it to the entries below. That's 0 now. And so we just have a 0, 6, negative 2, 0. And if you divide by 6 right here, that would have been even faster. But does that make sense to folks so far? Okay, so standard row reduction, but with a lot of shortcuts now, since we've done like hundreds of them at this point in the course. Another step is going to give us 1, 0, 0, 0, 0. Next, divide by 6. This will be a 1, negative 2, 6, or negative 1/3, 0, and 0, 0, 0, 0. That's always kind of a concern because you might have noticed the start of the book usually doesn't have fractions, but they show up a little bit more in chapter 5. They become kind of unavoidable. It's extremely hard to invent a matrix that is never going to produce a fraction here when you're going for the eigensystem. But so far, we can now say, well, we need a new page. Let's just say continues. We can call this x1, x2, x3 like before, and just go through the motions. This one's kind of interesting. x1, automatically 0 from row 1. Now for row 2, we can say x2, add a third x3 to both sides. It'll come out like that. And then x3 was the free variable, so x3 equals x3. That is the solution set to that equation up here, but we didn't quite like that format. Really, the major reason we've been pushing parametric vector form is so we can get the eigenvectors right away, or a basis for a null space, in other words. So we want to say x equals, take your x3, pull all the coefficients, they'll be 0, 1/3, 1. And the statement is optional, but it certainly helps. We can say where x3 is in R. So we're ready to paraphrase, or summarize rather. The next statement is for lambda 2 equals 4, the corresponding eigenvector is v3, 3 because it's our third eigenvector. And if you pulled 0, 1/3, 1 and dropped it right here, that's completely fine. You've got the right thing. But the back of the book would almost never do that. They make a specific choice on x3. Any volunteers for what they would probably do?
I think it's 0, 1/3.
Exactly. So if you put a 3 here for x3, multiply through, you get exactly as you said. 0, 1, and 3. And this is setting x3 equals 3. It's convenient because we've cleared the denominator right here. It's not necessary because we weren't doing anything additional with this matrix. But if this was a longer applied problem somewhere else, that's actually a pretty important step, because now if you're working with the diagonalization, you would rather have non-fractions here, just the nicest numbers you can come up with. So it's a best practice usually to pick a scalar that conveniently eliminates denominators as well. So we're just about there, folks. And if I zoom out just a little bit, I think we can put the answer together. This is what your answer would look like, whether it's in a final exam question or a question on the homework. I put here on the Moodle website to write your answers in the form A equals P times D times P inverse. So actually display the diagonalization. So this will look like this. A equals, we want a matrix P, but the color coding in chapter 5 has been pretty specific. If it's blue, we're talking about eigenvectors. And if it's green, we're talking about eigenvalues. So this is how it starts out. We put an inverse on this one, and then you don't have to calculate that. Very good reminder, because people have calculated it before in a final exam. And that's heartbreaking, because you want to spend all that time somewhere else doing the other linear algebra questions. There's already going to be a question on matrix inverses. You don't have to do it again here. The rest of it is kind of up to your choice. This one, lambda 1 equals 2, let's remind ourselves, this has multiplicity 2. That means it's going to show up twice on the main diagonal. But we expect it to, because there's 2 eigenvectors that go along with it. So if you to begin with this one, you'll go 2, 0, 0, 0, 2, 0. And now you need to plug these vectors down inside here. What's amazing, though, it doesn't even matter what the order is. It's all up to you. There are lots of different ways to diagonalize a matrix, infinitely many different ways. I would just go in order that it's written. 2, 1, 0, 0, 0, 1. Then come down here. Our last eigenvalue is 4, so plug that into the last column in the diagonal matrix. Then grab this one, 0, 1, 3. And we filled out 2 matrices, but whatever you have here, just duplicate it over here and you're on the right track. 2, 1, 0, 0, 0, 1, 0, 1, 3. And we did it, folks. We see the diagonalization, and that's where the problem would end. Any questions at all to that stage? Awesome. It's kind of an adventure in linear algebra. And if you look at this problem really closely, this reviews a lot of the course. Right here, we're reviewing row reduction, echelon forms. We're reviewing parametric vector forms. This is essentially a spanning set right here. So there's a null space. Everything kind of goes all together to get to that point, as well as finding eigenvectors, eigenvalues as part of the process as well. So this one question hits a ton of topics in linear algebra. It's kind of nice. But I think at this stage, we're just about done with the notes. Just a couple more concepts to go along with diagonalization itself. So those concepts go about like this. This was a question they were asking about earlier, Rajab, about the eigenvalues and invertibility and diagonalization. If you have an n by n matrix with n different eigenvalues, your matrix is all automatically diagonalizable, no matter what. That's kind of nice. And so this could be an exam question, but it's a dangerous exam question in a certain sense. I think when a lot of people see this problem, your gut reaction to it is, I've got to do this. We're coming up with a diagonalization. But that's not what it's asking about at all. It's asking, is A diagonalizable? So just a warning, if this question does come up on the exam, we do not have to diagonalize A. We're just wondering if it can be done or not. So that observation could save you like 15 minutes on the final exam. So watch out for the wording of the questions as well. I keep my wording very similar to how you've seen it on the lecture notes, which I tried to match as well with the actual homework exercises out of the book. So, well, to address this question, is A invertible? What would you folks say, yay or nay on invertibility? Absolutely. I mean, there's a lot of things you could say. Determinant is zero, columns are linearly dependent, but it's just definitely not invertible. Let's say here, really quickly here, that since there can be at most two pivots, and A is 3 by 3, A inverse does not exist. Kind of weird way to answer the question of honesty, but it's a cool concept to tie together. If you could just see the pivots, you can decide invertibility. But there's like a bazillion different ways to answer this question. Just pick your favorite approach on the invertible matrix theorem. You might have done a determinant, for example, would have worked just fine. So I decided to just emphasize the pivots on this one for no particular reason. The other question was, is A diagonalizable? And all you would have to do is say, A has eigenvalues, lambda 1 equals 0, lambda 2 equals 1, lambda 3 equals -1, all distinct, or all different. I'm just trying to match this part of the theorem. And so we can say next, and so A is diagonalizable. So it's a non-invertible diagonalizable matrix. And like we mentioned before, put a 4 there, still diagonalizable because you'd have a 4 here. Those are still distinct eigenvalues, but this one now is invertible. So that's the reason why diagonalization is not in the invertible matrix theorem at all. Kind of remarkable. So these are fast concept questions. If we decide when we write for the final exam, if I decide that it's getting a little too long, I might potentially take a question like this and turn it into a concept question. It all just depends on how the problems fall in. I haven't even written the final exam yet. But other questions so far? Okay, so that's diagonalization in a nutshell. At this stage, these are the most common final exam questions you could see. There's a couple more here, mainly to support the homework. And here's a gigantic theorem, theorem number 7. Our author has a knack for taking different elements of linear algebra and just putting them into one huge statement. So here's that statement. Let's walk through this and also say what part of the theorem is most important for the homework as well, because it's a huge statement. So we'll start off with saying A is of size n by n, and it has p distinct eigenvalues. Because of that p right there, p might be less than n, or it might be equal to it. So we don't necessarily know. If it's dead on equal to n, then what we do know is that the matrix is diagonalizable automatically. But this is the most we know about this. You can't have more than n eigenvalues. So that index of p says, well, it's got to be less than or equal to n. Now it says for a different index, k, as you go from 1 through p, that just means we're picking a specific eigenvalue on this list. The dimension of the eigenspace for lambda k is less than or equal to the multiplicity of the eigenvalue lambda k. It's a huge statement right there. Let's pause on it. Let me show you what they're essentially saying right here based on a problem that we have done. So once you find the dimension of the eigenspace, say like we did up here, this had one free variable, so the dimension of the eigenspace was 1, but we compared it against the multiplicity of lambda 1. We found the dimension is less than 2. All that theorem is saying is this cannot be larger than 2, where the 2 came from here. So that's all that theorem is trying to say. Dimension of your eigenspace is at most equal to the algebraic multiplicity. Has to use a lot of words just to say that because it has to be a precise statement. But does that make sense for part A? Okay, so moving on to the next part. Part B is also a really long statement, and it says, your matrix A is diagonalizable if and only if the sum of the dimensions of the eigenspace is equal to n. So if you count up the sum of the dimensions of the eigenspace and it equals that, then you've got a diagonalizable matrix. And we saw that too. Let's scroll up again just to consider this statement, the first part with the problem we did. That would be this one right here. So this matrix had two pivots. So one free variable, dimension of the eigenspace is one. One pivot, so two free variables, the dimension of that eigenspace is two, and A was diagonalizable. It's no coincidence that the sum of those dimensions is three, which matches the size of the matrix 3 by 3. That's what allowed it diagonalizable. We just had enough eigenvectors to match the size of that square matrix. So that's the content of that first part right there. And I would say for us, for the homework questions and for exams, this statement right here is the most important part. This is the biggest takeaway. I could have just put that statement there, but I felt like putting the whole deal the author gave us is nice just for the sake of completeness. But this is the most important part. It tells us the conditions of when we'll see if it's diagonalizable or not. And the subparts down below are just saying what happens if it is diagonalizable. The characteristic polynomial factors completely into linear factors. So, okay, had the dimension of the eigenspace equals the multiplicity. So again, if this happens for all of your eigenvalues, then you're in good shape. You have a diagonalizable matrix. If the dimension is less than the multiplicity, that's when we get the defective matrix like we saw. And finally, it says if it's diagonalizable, take all the bases for all the eigenspaces, put them together, and that will be considered an eigenvector basis for the space Rn. So these produce bases, they're odd looking ones, but they're the right kind of basis that matches the applied problem. But again, this is the major thing that we're going to look at. We're mostly interested in when a matrix is diagonalizable or not. That's a really long statement, though. It's kind of painful just to look at all those moving parts. Any questions about it whatsoever?
We only diagonalize square matrix.
Exactly. The reason for that is, as far as when it comes to diagonalization, the first thing you would need is to come up with the eigenvalues. But then that takes us back to section 5.1. The only way we can get eigenvalues is we require the matrix to be square from the very beginning. So we can only diagonalize square matrices because of that. Other questions so far? Okay, well, these are the last concept questions that you're going to see in the final homework assignment, assignment 22. Congratulations to getting to the very end. It's a lot of work, I'd say. All we're doing in example 7 and 8 is see if we can diagonalize the matrix that matches these conditions. The most important thing to look at is the size of that matrix, because you'll notice that everything is kind of based off n here, the size of your square matrix. We're told there's 3 distinct eigenvalues. So let's just list them out. There's a lambda 1, a lambda 2, and a lambda 3. They tell us next that one of the eigenspaces has dimension 2. Kind of hard to highlight. There we go. I don't know which one it is, so let's just say lambda 1 is the one. Let's say that dimension of the null space, A minus lambda 1, equals 2. That is a long statement to write out, but it's a good reminder. This is what you would do to diagonalize in the first place. You look at that null space. That means the rest of them have dimension null A minus, oh, hang on, let's fix something here. That looked correct at first, but there's got to be an identity matrix, or that whole expression wouldn't even make sense. So that dimension is equal to 2. The dimension of this one, let's see here. This one had dimension 2. There's 2 more to take a look at. They didn't give us very great information on the last 2. But what you could do is start writing stuff down. It seems like 1 and 1 would make sense, right? there's got to be an eigenvector that corresponds to your eigenvalue the moment you find one. But some people might wonder, why can't I put a 2 on this one? If this one was of dimension 2, this one might be dimension 1, but the sum of these is 5, and that's actually impossible. You can't exceed 4 right here for the dimensions of your eigenspaces. So it looks like we're constrained. The dimension of this one has got to be a 1. Dimension of this one has got to be a 1. And where can we help ourselves out with seeing that? The dimension of the eigenspace is less than or equal to the multiplicity of the eigenvalue. We don't have information on these multiplicities, but that means no matter what these multiplicities are, these are going to be less than or equal to 1. Let me just tally these. We have dimension 4, which matches the 4 up here, which implies A is diagonalizable. The sum of the dimensions of the eigenspaces, in other words, equals 4. And that's all we needed to diagonalize that matrix. Any questions there, folks, with running through that one? Okay, example 8 is a little bit worse. It has 3 distinct eigenvalues. It's of size 5 by 5, so we have to pay attention to dimension 5. But what makes this one a little bit worse is the way the question is asked. It says one eigenspace is 2-dimensional, another is 1-dimensional, but we are wondering, is it possible that A is not diagonalizable? It may or may not be, but we're wondering, is there a way it could potentially be defective? It's kind of a tougher question to ask, so let's run through it carefully. Let's see, 3 distinct eigenvalues. So we have a lambda 1, lambda 2, lambda 3. What else do we know? One eigenspace is 2-dimensional. Let's say it's the first one. Dimension of the null of A minus lambda 1 I is 2. So there's our 2-dimensional eigenspace. This right here is the eigenspace. That's kind of nice. Another one is 1-dimensional. Let's call it lambda 2. So the dimension of null A minus lambda 2I. They just told us specifically that's dimension 1. Now we have no information on this one right here, but we can never exceed 5. So whatever this dimension is, it could be potentially 2. If it's 2, the sum of these is equal to 5 and it's diagonalizable. It can't be 3 though. We cannot exceed the value of 5 for the sum of dimensions, but it's possible that that one would be equal to 1, right? And if that's the case, let's say here, dimension of null A minus lambda 1, or excuse me, 3, not sure why I went backwards, can potentially equal 1. That's the minimum that any eigenspace dimension could be for any eigenvalue. So if it has the potential to be 1, and we sum these all together, we have dimension equal to 4, which is less than 5, the size here from the matrix, which would say A can, again, we have to say potentially because we don't know if it's 1 or 2. It just has the potential to be 1. So A can potentially be, you could say not diagonalizable, or you could say defective, your call. Let's match up the instructions here and just say not diagonalizable. Well, we did it, folks. That's the end of the content on this one. Any questions at all with the 2 concept questions there? Okay, the major takeaway with these last 2, it's more about if you ever come up with this situation right here, where you're trying to diagonalize a matrix, definitely start at the highest multiplicity. And the moment you notice the dimension is 1, just stop. The problem is over. If 1 is less than 2, then that whole thing is defective. You don't have enough linearly independent eigenvectors. But it takes a lot of precise writing, I mean, look at that, to convey all that information. If you're doing it as a homework problem in linear algebra and finding the matrices are defective, then you're on the right track. Well, let's save this up. We have completed chapter 3. There's a lot more going on in chapter 3, so if you're interested in applications, the book just keeps on going and going. Too bad it's not like a 9 credit class. We could finish the whole book with all that time. But for the last thing we're going to do this semester is look a little bit into section 6.1 on the geometry of the geometry of vector spaces. I think I got used to just saying eigenspaces. We lost a couple days. I think I took a sick day. There was snow days, all sorts of stuff happening at the start of the semester. So we didn't quite get to section 6.2, 6.3 like we typically would. If you're curious on that content, I'll post the notes down below, just so if you want to know what they look like, how it goes, you'll have an idea of it. So let's go to section 6.1. After we finish off, oh, that's the wrong section. You would stop it right there. No, you cannot. Let me just close it out. After we finish section 6.1, which will be next Tuesday, we'll just immediately launch into reviewing for the final exam. It's kind of a light section, in all honesty. A lot of people have done inner products when they come to this class already, especially if you've done Calculus 3 work, you've done a lot of inner products potentially. So this is a set of notes that kind of just gets everyone on the same page. But as you scroll through the content, it starts getting weirder and weirder and weirder, as linear algebra always does. It starts off nice, but then gets abstract. What we want to really do is find angle between vectors. We are really earnestly going for the geometry of vector spaces. So we're interested in orthogonality. We can also use this equation to find the angle between any two vectors. And notice any vector space can have an inner product. So you can ask about what is the angle between square root of t and t squared in a functional space. That's really kind of bizarre, but it can be done. And this is where the content will end on these theorems down below. Our author didn't say too much about these theorems, but I feel like it's almost a disservice. Theorem 3 is one of the deepest results that we've seen in linear algebra in this entire course. And this is sometimes called the fundamental theorem of subspaces. Much like there's a fundamental theorem of arithmetic, a fundamental theorem of algebra, a fundamental theorem of calculus, if we had to put down a fundamental theorem in linear algebra, most people would agree it's this right here. That's an incredibly deep insight. So our goal is to get to this problem. And example 8, let's say just as a hint on the final exam, something like this is a guaranteed final exam question. It's actually not too tough to do, but it's abstract. We have to know how to do it. So we'll do some careful work. We'll probably do this one on Tuesday. There's work to get there, so let's just crawl through the results here. This is the getting everyone on the same page side of the result. Starts off kind of fun. It's not too abstract yet. You grab any two vectors in, say, Rn, an n-dimensional vector space, our dot product. Calculus would often call this dot product, so would a lot of engineering physics settings. Linear algebra typically calls it an inner product, but they're synonymous for us. The inner product of u and v is denoted this way. And notice that already looks kind of sketchy. You might have saw that it's in linear algebra. We have never taken a vector times a vector necessarily. We've actually done this one right here in chapter 2. That works because if you transpose this vector, what size was it? It's of size n by 1. So over here, you transpose is size 1 by n. The vector b is of size n by 1. So that's an actual compatible multiplication right there. The inner dimensions match, but the outer dimensions are 1. And that's a way to say the results right here is a scalar. That's kind of an unusual operation. We're taking vectors out of a vector space and getting a scalar out. So there's another concept going on along here. If you thought infinite dimensional vector spaces are interesting, this is a very close example to something called a functional. A functional, as long as we keep one vector fixed, is something that takes a vector like this one from a vector space, does an operation, and gives you a scalar back. So this is a functional, and this is an example of an entire discipline in linear algebra called functional analysis, where you're analyzing vector spaces like let me get a spot here. CAB, this one doesn't have a finite basis, it's a dimension infinity. And it's these functionals that help us understand those kinds of vector spaces a little bit better. So there's a lot to say about the inner product really, but for here, we're just going to calculate one to see how it goes. So here's two vectors out of R2. Let's calculate U dot B to start. And we've done this a lot of times actually. And anytime you did a matrix times a matrix, the entries you're producing are actual on dot products. If we followed the instructions to the letter, we would take the transpose of this vector U. That just means write it sideways, 3, 4. Keep the vector V exactly as is, 2, -3. Multiply these as if they're matrices, just like in chapter 2. In fact, you can regard them that way. You'll get 6 minus 12, resulting in the scalar of -6. And that's it. That's our dot product. Compared to what we've done so far in linear algebra, I'd say this is kind of relaxing in a way. Any questions about it though so far? Okay, this one looks a little bit worse because it's just a more built up expression. It's saying take U dot B, multiply by B, but recall U dot B is a scalar now. It resulted in -6. So this is just saying take -6, rescale B, which is 2, -3, and you get -12, +18. It's actually kind of tricky. This one's a scalar. This one is an honest vector back in R2 because you're just rescaling B. But there they are, two fast operations. Any questions, folks, with those dot products so far? Okay, so we're going to start building on this more and more. Now that we have something that you could regard as an inner product, we can take, let's say it this way, we can now take the vector space R2 or any vector space P2 CAB. As long as you define an inner product, we can convert it or upgrade it, or with the extra operation, we can take the vector space R2 and call it an inner product space. And inner product spaces are extremely important, not just in linear algebra. If you're going along the lines in mathematics of, say, engineering mathematics, you're going to be working with things like Fourier series. At Fourier series, you're just really honestly working in inner product space. Inner product spaces are what develop those kinds of tools. So that's already kind of weird. Linear algebra is intersecting with a lot of stuff. But it gets even more interesting. The reason we can do calculus in a 3-dimensional space, 4-dimensional space, or higher is because we have geometry on those vector spaces, and it's the inner product that gives us all of the geometry. So somehow, some way, this silly little operation gives you every ounce of geometry you need for calculus to work on R2, R4, or even P2, for example. You can develop calculus on that as a vector space. So going down below, here are the properties you would have for any inner product space. But there is one strong takeaway. These things don't go the same exact way if you're working in a complex vector space. So let's put down here just as a quick statement. Theorem 1 is false in Cn. So in other words, we want vectors that have only real numbers with our inner product space. If you allow complex numbers, well, this theorem has to change a whole bunch. That's pretty advanced linear algebra. We haven't even really touched on complex numbers at all, but they can come up. We saw them come up with eigenvalues here and there. But here are the list of things that you can take for granted for the inner product itself. First is symmetry. U dot V is the same as V dot U. Doesn't matter the order you take your inner product. It does over here. So watch out for this thing in yellow if you're going to take more linear algebra. This one's a nice property of distribution. If you're adding two vectors and you're taking the dot product, well, you could either add the vectors first or just take the dot product of the individual vectors and then add. So that's kind of a nice little property. This one with result to a scalar says if you scale U and take the dot product of V, that's one option. You could just do U dot V first and then rescale the result by C, or rescale V, up to you, and then take the dot product of U and the scaled vector V. All this is really saying is C commutes in a pseudo-commutative kind of way. You can put your scalar C wherever you would like. That's nice. The last result is actually pretty important. This one is called, let me see if I can put in extra space. If it's important, we should make sure we're highlighting this. This property is called positivity. And when you tack on this property, part D is called positive definite. So it says, no matter what vector U, if you take a U dot product with itself, you're never going to get a negative value. It's always positive, potentially zero. But if it did come out to be zero, your original vector had to have been the zero vector from the very start. So that's what this whole statement is saying. It says prove part D of theorem 1. But you know what? I'll leave that up to you guys. Should we prove it or move on to the next? Your choice today. Move on? Okay. We voted to skip it. No worries. Yeah, go ahead.
So why does multiplicity work here when in our previous section it didn't?
What do you mean by multiplicity? Do you mean the...
Sorry, no, not multiplicity. The commutative properties that we're seeing here.
It's all because of the size of these particular values right here. And that's a good question because, like you were mentioning, with matrices times of matrices, commutativity falls completely on its face. But I think a better explanation is, for part A, if you take U equals U1, U2, all the way down through, say, UN, take another vector V equals V1, V2, down to Vn, then here's what we can allow happen to prove part A right here. So take U dot V, and all we're doing really is taking the corresponding entries, multiplying them and adding them together. It'll turn into U1 times V1 plus U2 times V2, all the way to UN times Vn. So that's the definition of the inner product. But once we get down here, because we have vectors in R, all of these are actual honest real numbers now. And real numbers have the commutativity. So that's where it starts to work out. You could just take this whole equation, use commutativity to write it as V1U1, V2U2, VN-UN, because V comes first right here, this would be V dot U. So we've turned it all around. Commutativity works for sure if it's just vectors like these. But if it were matrices, full-on matrices, it would have broken down. Does that make sense for that question there?
Yeah.
Awesome, thanks for that question. That's a really important one because it's easy to lose sight of all the things that went wrong in chapter 2, but suddenly we have nice properties we're taking advantage of. So that's a deep question as well. Other questions so far, folks? Okay, well, let's now take a look at the next thing. These are all the properties that we take for granted when it comes to inner product spaces, but we will be using some of them. We're going to be using parts B and C, I believe, in the problems to come. So we'll scroll up to that when it comes up. Here's the next thing you'd want to develop if you're trying to get calculus to work for you in a vector space. And that's what chapter 6 is actually all about. Developing an inner product space is trying to get into calculus, Fourier series, and all that great stuff. The thing that comes up a lot in calculus is the norm of a vector. I usually say norm, but it's completely synonymous with saying the length of the vector. The norm of a vector is denoted this way. Much like absolute values, we double them up to say this is not a scalar. We're taking the absolute value or norm or length of an honest vector now in Rn. So that's the notation we typically use, the double bars. The way it's actually calculated is the norm of V is just the square root of V dot product with itself. Notice positivity is already important there. Let's screenshot it real quick. The only reason this definition works is because inside that square root can never be a negative number. And that's because v dot v or u dot u is strictly a positive quantity or zero potentially. So that means this is a well-defined definition here. We can now say that the length of a vector v is the square root of its dot product. And if the length was 1, we call it a unit vector. And let's say even more, the process of rescaling a vector so that the length of that vector v is 1 is called normalizing or taking the norm of v. So that's something that we do quite a lot in a calculus setting. Normalizing a vector. Unit vectors are just easier to operate with if you're taking directional derivatives or any kind of weird thing like that. The theorem down below is just a nice little mathematical fact. If you ever have to take a norm of a rescaled vector, you don't need to work as hard as it might look. You just factor out that vector or that scalar c, take its absolute value, and do the norm of u right here. So those are our new definitions, but again, these are probably familiar to a lot of people. Any questions so far? Okay, well, let's try this all out for a new example. We have something in R2, just a simple vector, 1, -2. We want to find a unit vector u in the same direction as v. This is essentially a calculus 3 problem, like straight up, this is calculus, something you would do in calculus 3. But let's visualize it. The vector v goes right here, so it's at 1, -2. Here's v. We want a unit vector that is in the same direction as v. I think that wording is kind of foggy if you've seen it for the first time. So let's add a little bit more. Here is a subspace of R2. That subspace is span v. When we say in the same direction as v, it means we want to be on the same side, but somewhere on this line. And it's got to be a unit vector at the same time. So that means we were looking for a vector u somewhere. It wouldn't be here because that's going to have a length longer than 1. Because right here, the y-coordinate is already a -1 there. It's probably going to be somewhere more like around here. That's where the unit vector we're trying to find would exist. How do we find it? Well, we first have to look into what is the length of v. So let's take a norm of v like this, which means we're doing the square root of v dot v. The dot product of v with itself essentially just boils down to square the entries and add them together. So that's a 1 squared plus a -2 squared. The whole thing turns into just a square root of 5. And so now we know the length of v right here. If we want it to be a unit vector, here's what we'll say. U is going to be 1 over the length of v, rescaling v. So that does the job for us. So this will turn into 1 over the root of 5, multiplying 1 -2. And this comes out as 1 over root 5, -2 over root 5. So my claim is that's exactly where this point would be. And it's a unit vector in the sense that the length of that vector should be 1. I don't know if you believe me, but there it is. Any questions about it so far? Okay, seeing is believing, so let's double check that. I'll put it in the pencil tool, so this is our check right here. Let's take the norm of that vector u. It had better come out as exactly 1. But notice it seems plausible. 1 -2/5 does place it in this quadrant 4 right here in the plane. But if we're normalizing or taking the norm of u, this would be the square root of this times itself, 1/5, plus this times itself, that'd be 4/5, which turns into the root of 5/5. But that's the fancy way to say square root of 1, and that's a fancy way to say 1 as well. So we really did it. We have a vector u. How do we know it's in the same direction? It's because we rescaled v. If you rescaled v, u is guaranteed to be in the span of v. That's all the span of V is, every linear combination of V. And if it's just one vector, that's a linear combination right there. So we did it, folks. That's the process of finding a unit vector. Really, this is just a fun example to just discuss what we mean by the norm or length of a vector. And we did a little bit more along with it. Any questions at all about it so far? Okay, and because I put a theorem down, it just seemed weird not to use it. So let's also calculate the norm of -82 times V. You could just rescale this by -82 up above and below, do the same process, square those entries, take the square root. The downside is you're going to have a square root of a very large number that's hard to simplify. But if you use this theorem up here, then you can say that the norm of -82V is just the same as taking the absolute value of -82, multiplying it by the norm of V. And that's working smart because now we don't have too much to do. That's 82. The norm of V we already calculated to be √5. And so there's essentially nothing to do in this problem since we already knew the norm of V. This could be a long, drawn-out approach with lots of arithmetic you're doing here. But that's the power of a good theorem. It just allows you to calculate extremely fast. Well, that's about all I have to say about these things. And I just noticed that the clock is ticking down. We ran out of time as well. Sorry for going a minute over, folks. When we come back, we're going to be looking into matters of finding distances, which gets us into finding angles between vectors. But any questions at all, folks, with where we ended? Okay, sorry for stealing a minute of your time. We'll refund it next Tuesday. But have a great night, folks. If you have any questions, don't hesitate to ask.
I keep thinking it's 650 for some reason.
Oh, yeah.
So,
Yeah, I think for me, I just kind of get excited about the problem. I don't want to stop talking about it, so I just forget that there's a clock here.